And now, let's move on to partial orders. So this is our second very important type of relations. Partial order and we will define it similarly to an equivalence relation just by demanding that it satisfy some of our basic properties from last time. A partial order is a relation that is reflexive, anti-symmetric this time, and transitive. So you will notice that these two properties are the same as for an equivalence relation. The only difference is that we have placed symmetric with anti-symmetric. But this is a big difference because you can kind of imagine that asking your relation to be symmetric is more like it is telling you that things are related. They're like related in the sense of being more the same. And asking that it is anti-symmetric is asking that they are related in a way that is more like separating them. And this maybe you can also understand in terms of our anti-symmetric relations were the ones that were less than and less than or equal to, which are things to do with ordering. So one more piece of notation. A set with a partial order is naturally called a partially ordered set. Or it can be shortened to poset. So that's the word that you may hear. So let's see some examples. So we expect it to be something like an order, but let's first note that this is not a partial order because it is not reflexive. So our orders are required to be more like less than or equal rather than strict less than. And these others, divisibility and congruence, are not anti-symmetric. So they're also not partial orders. The one example we have seen is that less than or equal to is reflexive and anti-symmetric and transitive, so it is a partial order. On any set that you choose to do it on, so for example, the real numbers with less than or equal to is a partially ordered set or poset. Although there is one other example that we can do already. Divisibility is anti-symmetric if we restrict to positive integers. Because remember, if A divides B and B divides A, then B must be plus or minus A. So restricting to positive integers eliminates the other possibility, and we get that it is in fact anti-symmetric. Because remember, anti-symmetry means that if A is related to B and B is related to A, then they must be equal. So positive integers with divisibility is also a poset. So let's introduce some notation for dealing with these things in general. We'll think of these as being some kind of ordering, although they won't necessarily be what you traditionally think of as an order. For example, we already have this example where divisibility is not exactly what we mean by ordering traditionally, but we'll use this sort of curly less than or equal to sign to mean the relation in a partially ordered set. So A curly less than or equal to B means A related to B in a poset, and A curly less than B means A is related to B, and A is not equal to B. So let's look at these two examples that we have so far of partially ordered sets. There is an important difference, which we can capture in the following definition. Say two elements in our partially ordered set are comparable if A is related to B or B is related to A. They are incomparable if not, if neither of these things is true. And for our partial order as a whole, if any two elements are comparable, by which I mean if every pair of elements is comparable, x and y are comparable for all x and y, then we call our order a total or linear order. So for example, this is something that distinguishes our two examples so far. For any A and B real numbers, it is true that either A is less than or equal to B or B is less than or equal to A. This is a fact. So R with less than equal is not only a partially ordered set, it is a totally ordered set. Oh, just enough space. How good. On the other hand, positive integers with divisibility is partially ordered, as we have seen, but it is not totally ordered. Meaning that there is some pair of elements which are incomparable. And in fact, in this case, there are many examples. So for example, 3 and 5, 3 does not divide 5, and 5 does not divide 3. So 3 and 5 are incomparable. So this is starting to show you that partially ordered sets can be much more general types of orderings than the usual linear ordering that you get in a linearly ordered set.